Welcome everyone to the class of marketing research and analysis. We were in the earlier classes we were continuing with the non-parametric test, and we discussed that non-parametric test is one test which is used when the data is distribution free or the data does not follow a normal distribution, right. Some of the non-parametric tests that we had done in the last class was like the Mann-Whitney U test, which was a which can be compared with the independent sample t test in the parametric with the parametric one, and the Kruskal-Wallis test similarly like the one way analysis of variance, right. Then we did the runs test, which was used to check the randomness of factor, right, the occurrence of a variable or a product, right. So, we wanted to measure whether it is random, it is a systematic occurrence or a random occurrence, and if we said it was, if it is systematic in occurrence, then we would have to take care of the problem, right. So, then we also did the sign test, in which we tried to see whether we tried to check the some of the hypothesis of a non-parametric measure. But we said that sign test is not a very powerful test, right, and it has its own limitations, and in comparison there is a more powerful test which is the signed Wilcoxon signed rank test, right. So, today we will be dealing with it. One more test that we had done was the association test, which is very close to the Pearson correlation, and which in non-parametric ones we say the Spearman correlation. So, the Spearman correlation was a non-parametric correlation method which we are for the non-parametric values, which we had adopted and found out how you should find out the association between two variables when the data is in a non-normal nature. So, today we will start our lecture with the Wilcoxon test, which is called the signed rank test, right, signed rank test. So, Wilcoxon signed rank test is a very popular test. So, we had just started in the last class. What it says is a non-parametric procedure for analyzing data from a matched sample experiment. So, basically when there are two pairs of sample, you are using this test, right. So, it uses quantitative data, but does not require the assumption, this is important, that the differences between the paired observations are normally distributed. So, it is not normally distributed, that is why non-parametric. The Wilcoxon signed rank test is used for at least ordinal in scaling. So, the data has to be measured in an ordinal scale. So, then only you are it is eligible to use the Wilcoxon test, right. So, when a researcher, what is the condition? When a researcher wants to analyze two sets of data obtained from the same individual, the appropriate test is applied is the related t test, right. So, which we say is a paired sample t test, which we use for a parametric, right. So, here similarly we use the Wilcoxon. However, when there is an extreme violation of the normality assumption, the Wilcoxon test can be used, right. So, the assumptions of this test are the scale of measurement within each pair must be at least ordinal in nature, the differences in scores must also constitute an ordinal scale. So, these are the two assumptions which we have to follow before we go for a Wilcoxon signed rank test. So, this is the example we had just started. So, this is a manufacturing firm which has got around 11 workers in this case. They are using two methods, they are method A and method B, right, of of producing, right. So, what it says, using a matched sample. So, it says here consider a manufacturing firm that is attempted to determine whether two production methods, method A and method B, differ in terms of the task completion time. So, is there a difference in the task completion of when somebody adopts method A versus the method B is to be found out. So, what they have done is they have done 11 randomly selected workers were chosen, and they were asked to do the work two times, once using method A and the other using method B. The production method that the worker used first was randomly selected. So, the worker was free to select any of the method from on his of his choice. The completion times for the two methods and the differences between the completion times are as shown below as in this table. So, you see, for example, if you take it in it is unitless at the moment. So, 10.2 seconds or 10.2 minutes you can take wherever. So, let us forget it the units. So, it is let us say worker A took for the first worker took 10.2 let us say seconds by using method A, and the same worker has used 9.5 seconds. So, that means he has taken less time by using the method B. Similarly, worker 2 has used 9.6 seconds here, 9.8 seconds by using method B. So, method B worker 2 is taking more time by using method B, whereas method worker 1 has taken more time with method A. Similarly, the third worker has taken more time with A, fourth worker has taken again with more time with A, fifth worker has taken more time with B, sixth again A, seventh A, eighth there is no difference, right, this is both are same. Ninth, if you see it is again A, 10th A, 11th A. So, the difference in the timing is recorded here. So, 9.5 10.2 minus 9.5 is 0.7. So, if it is positive, that means we understand that since it is A minus B, so we understand that A takes more time, right, the method A takes more time. So, if it is minus, then we understand that the method B takes more time, right. So, this is the simple thing that we have done, and the difference has been found out to be like this. A positive difference indicates that method A required more time, as I just said. A negative difference indicates that the method B required more time, right. Do the data indicate that the two production methods differ significantly in terms of their completion times? So, this is of significant interest to the researcher, and in fact there are several situations in life where you might have to compare two methods of production or two methods of teaching, or you might have to several experiments can be done with such kind of options. If we assume that the differences have a symmetric distribution, but not necessarily a normal distribution, the Wilcoxon rank test applies, right. So, it is not a normal distribution, we have said. In particular, the Wilcoxon sign rank test for the difference between the median completion times for the two production methods. So, what it does is, it does not, as I have said earlier also in my earlier class, the in case of a parametric we use the mean, right. In case of a non-parametric we use mostly the median, right. So, here also when we make our hypothesis, if you see the null hypothesis, what it says that the median time for completing the work using method A is equal to the median time of completing the work by using method B. So, the median for method A minus median for method B is equal to 0, right. But that is not of the interest, right. So, any worker or any supervisor or any manager or any researcher, he is not interested, he is interested to see that there should be a difference. So, what is the difference? The alternative hypothesis states the median for method A is not equal to the median for method B, okay. So, if H0 the null hypothesis cannot be rejected, we will not be able to conclude that the median completion times are different, right. However, if alternate is accepted or H0 is rejected, we will conclude that the median completion times are different. Obviously, what we are doing? We are using a 0.5% level of significance, right. The first step is to, if you go back to the table, there was one time for the worker 8, can you see this, and here the worker has taken similar time for both by using method A and method B. So, when such a case occurs in this kind of a test within the Wilcoxon test, it is necessary to discard that particular element or that particular case, right. So, the first step is to discard the difference of 0, in this case the worker 8, and then compute the absolute value of the differences for the remaining 10 workers, okay. Now, what do we do next? The next is we rank these absolute differences from lowest to highest. So, the one which is the lowest difference in time is the first rank, the highest difference in time is the last rank, the 10th rank in this case. So, the smallest absolute difference of 0.1 for worker 7 is assigned the rank of 1. Similarly, the second smallest absolute difference of 0.2 is assigned the rank of 2. This ranking of absolute differences continues with the largest absolute difference of 0.9 for worker 6 being assigned the rank of 10, right. So, let us see this table. So, for example, the difference is here, right. So, here the absolute difference we are making it irrespective of any sign. So, it is all positive. So, 0.7, 0.2, 0.4, 0.5, 0.4, 0.9, 0.1, 0.6, 0.5, 0.8, right. Now, if we have to rank, let us say we have to rank, I think I have done it in the next slide, I think, yeah, I have done it better here. So, if you look at the order difference first of all, which is the lowest out of the lot, now 0.1, we will only consider the absolute differences. So, 0.1, then what is the next 0.2, right. So, 0.2, so we are keeping the with the negative, no issues. Then 0.4, then again there is a 0.4, this is 1, this is 1, right. So, again a 0.4, then 0.5, then 0.5 again, right, then 0.6, 0.6 next, then 0.7, this is the one, right. So, this is discarded, so it is not to be counted, then 0.8, so this is coming here, right, and finally 0.9, the difference with the worker 6 is coming here, right. So, this is the difference arranged in a order. Now, let us give a rank. Now, how do we give a rank? So, the first thing is the first one is gets a first rank, the minimum difference, the second one gets a second rank, but now you see there are 2 people at 0.4, taking the absolute difference as 0.4, they are in the position 3rd and 4th, So, here the ranking will become now 3 plus 4 by 2, so 3 plus 4 by 2, so I will write it here, 3 plus 4 by 2 is equal to 3.5. So, both get a 3.5, right. The next is 5.5, the next is 5.5, let us see. So, what is happening here now, if you look at this value, what is coming up, which number is this? So, 0.5, 0.5, right. So, 5 and 6, so 5 plus 6 by 2, so that is equal to again 5.5, and there are for 2 cases, so 5.5, 5.5. So, the next is once you are done with it, then the 0.6 which gets a 7th rank. So, 1, 2, 3, 3.5, 3.5, this is 3 and 4, 5 and 6, then 7, right. Then this is discarded, then 8th rank, right, then the 9th rank, and the finally the 10th rank, right. So, all the ranks have been given now, right. Now, the question is, now let us see which of them are fall into the negative category. So, this one has a negative value, this one has a negative value, these two, right. So, the second rank and the 4th rank, they have a negative value. Now, if you look at the positive rank similarly, it is 1, 3, 5, 6, 7, 8, 9, 10. So, if I add the ranks for this, if I add, which I am saying is W, the total weight is 5.5 for the negative ranks and 49.5 for the positive ranks. Now what? Now what will you do? How will you proceed from here? Let us see. So, what is the inference drawn? The critical value from the table for a two-tailed test with n is equal to 10. Now, what is this n? So, the n is here 10 because one person has been discarded, right. So, remaining is 10. So, I will show you, I have brought the table also, I can show you, or you can just follow the Wilcoxon table, right, where it says with a particular number of sample size, what is the value, right. So, the critical value for a two-tailed test with this is obviously a two-tailed test because it is not equal to case. So, it can fall anywhere to the right or left, we do not know, is 8 actually, right. So, if W, that means the weight, right, this weight 1, 2, this weight is less than or equal to the critical value, reject the null hypothesis. Now, the question is, here we are saying W, but here we are having 2 W's, right, in fact one for the negative rank, one for the positive rank. So, which one would you select or keep in during your study? So, always keep the one which is the lowest out of the 2. So, in this case which is lowest? Lower, the 5.5 and 49.5. So, obviously the 5.5 is a lower rank, right. So, we will compare this 5.5 with the value of 8, right. In this case 5.5, which is the value, is lesser than the critical value of 8 for a sample size of 10. So, the null hypothesis is rejected. We reject H0 and conclude that the median completion times for the two production methods are not equal. Let us see, that is what we had written. Let us go back. So, median for this is rejected. So, this is accepted. So, median for method A and median for method B is not equal, that is what we were saying, right, are not equal, right. So, now which is then takes more time. So, let us go to this with t plus the time being in the upper tail of the sampling distribution, we see that now let us go back. Now, here it is 49.5, right. So, the rank, now this is obviously if you look at the time it takes more time. So, the t plus being in the upper tail, we see that the method A led to the longer completion times, just go back. So, if you look at the difference, right. So, in which we said that if you look at the difference is positive, then we say A is bigger, if it is negative B is bigger, right. So, in this case we see it is more of positive, right. So, that means what, if you look at these differences and this from here we see the positive rank is more. So, that is why we say obviously the A has taken more time than the B, right. So, the method A, when production the workers are using method A, they are consuming more time than the method B. So, we would expect management to conclude that method B is a faster or better production method and A takes more time than B, right. This is method. This is another way of also doing the same problem which I have said as method 2, and I will show you how to do that, the Wilcoxon signed rank test. Now, let us see, let T plus denote the sum of the positive signed ranks, which is 49.5, right. To conduct the test, we use the test statistics. If the median of the two populations are equal and the number of matched pairs is 10 or more, the sampling distribution can be approximated by a normal distribution. So, in our case it is 10, right. So, how do you calculate the mean in such a condition? The formula is n into n plus 1 divided by 4, right. This is the mean you calculate, this is the standard deviation. So, because we require to calculate the z, right. So, to calculate the z, now you require the mean and the standard error, right. So, now let us see what is the mean. The mean has been 27.5. So, 10 is n is 10. So, 10 into 10 plus 1 divided by 4 gives you 27.5. What is the standard error? The standard error is n into n plus 1 into 2n plus 1 divided by 24, which comes to 9.8107. Okay. So, we have the two values, right. Now taking these two values, we can calculate, you see the what is said, the discrete probability at t is equal to 49.5 is approximated by the normal probability interval 49 to 50, that means it lies between 49 to 50, and it is approximated by p is equal to, so that means we are calculating the z here, z is greater than equal to 49, approximation value has been taken, the lower one 49. So, 49 minus 27.5. So, this is as good as if you remember x minus mu, right, by standard error, right. So, this is coming to be z is greater than equal to somewhere around 2.19, right. So, if z is equal to 2.19, what does it mean? So, let us see. So, it is a two-tailed test, So, we see that the two-tailed p value is equal to how much? Now, the area under the curve for when z is equal to 2.19 is 0.4857. So, this area is 0.4857 for this side, 0.4857 for this side, right. So, what is remaining? So, 1 minus this 2 into, obviously we have multiplied two sides. So, is 1 minus this much comes 0.286. So, this plus this value and this value is coming to be 0.0286, and we have taken a significance value of 5%, right. So, now this value is this p value, and comparing with the significance value we have taken. Now, if you compare, we will see that this calculated value is lesser than the table value or the significance value. In this case, since it is lesser, so we know from beginning that when it is lesser, we will reject the null hypothesis. So, we reject H0 and conclude that the median completion times for the two production methods are not equal, the same thing we had got earlier also. So, we see that method A led to the longer completion times, and we would expect management to conclude that method B is the faster or better production method. So, I hope the Wilcoxon signed rank test is very clear to you, because both the methods you can utilize and understand and make a inference, right. So, this is the one thing that we have done, and it is a very powerful test, much better than the sign test, which is not so powerful. In comparison, the Wilcoxon test is a much powerful test, right. Okay. I will show you how to run this test also on the software, maybe little later on, right. So, the next is what we will start with is another test called the chi-square test. Now, what is this chi-square test? Chi-square test is another non-parametric test which has a very large utility, and it is utilized in order to compare data which are collected in a nominal manner, right, in a nominal way. Okay. So, let me just see if the data is available. No, we have not, I will show you later on. So, what is this chi-square statistic or chi-square test? The chi-square test is denoted as chi-square, is used to test the statistical significance of the observed association in a cross tabulation. Now, in a cross tabulation we have seen many a times the use of cross tabulation is very high, but then it does not tell us whether the association is significant or not. So, in a chi-square statistic or a test, we use it to check whether the data we have got or the results we have got can be termed as significant or not significant. It assists us in determining whether a systematic association exists between the two variables. Chi-square statistics is a very powerful technique, because it tells about two important things. One is the association and the other is the goodness of fit, right, which I will explain both the things in this lecture, right. Goodness of fit test. Okay. So, what is this chi-square statistic? The chi-square statistic is given by the formula. So, chi-square is equal to summation f observed, that means observed frequency, minus expected frequency square divided by the expected frequency. This is the formula. So, f is the expected cell frequency, fo is the actual observed frequency. The null hypothesis is that there is no association between the variables. So, there is no association between the variables, this is the null hypothesis. And what is the alternate? Obviously, the alternate will be that there is an association between the variables, but we do not know what is the association like, but there is an association. This test is conducted by computing the cell frequencies that would be expected if no association were present between the variables, right, given the existing row and column totals. So, suppose we say something looks like the income of people versus the cleanliness, right, cleanliness. Okay. So, high income, low income, let us say people can be very clean, hygiene oriented, or not so clean, right, not so clean. So, now when this is the row total, these are the row total, this is the column total, right, okay, and you have a grand total out here. So, this what it says is these expected cell frequencies denoted as FE are then compared with the actual observed frequencies. So, you have an observed frequency. Now, how many people are actually from a high income group and who are very clean, let us say x, or let us say let us give a number 10, let us say high income group not so clean, let us say is 5, low income group very clean is let us say 9, low income group not so clean is 3, let us say. Now, from here is there an association between cleanliness and income? That is what we need to find out. So, it helps in the to calculate the chi-square statistic. The greater the discrepancies between the expected and the observed frequency, so higher the difference between the expected frequency and the observed frequency, the larger is the value of the statistic, and it is not a very desirable thing. Assume that a cross tabulation has R rows and C columns and a random sample of n observations. Then the expected frequency for each cell is calculated as like this. So, how is it calculated? Now, let us see this R1 let us say R2 R2 T2, C1 T1, C2 T2 and this is grand total. Now, what you do is you write it like this R1 T1 right into C1 T1 divided by the grand total, right. So, where NR is the total number in the row, total number in the column NC and total sample size is the N. Okay. To determine whether a systematic association exists, the probability of obtaining a value of chi-square as large or larger than the one calculated is estimated. The important characteristics of the chi-square statistics is the number of degrees of freedom associated. Now, generally we know that the number of degrees is written is equal to the number of observations less by the number of constraints, right. So, generally it is n minus 1 in many cases, right. So, n is the sample size minus 1, but here it is slightly different. In this case of a chi-square statistic, the number of degrees of freedom is equal to the product of the number of rows r minus 1 less 1 and the number of columns less 1. So, r minus 1 into c minus 1, this is our degree of freedom. Okay. The null hypothesis of no association between the two variables will be rejected only when the calculated value of the test statistic is greater than the critical value of the chi-square distribution. What is it saying? The null hypothesis of no association between the two variables will be rejected only when the calculated value is greater. So, your critical value is here, if your calculated value falls here then you reject, right, you reject, but suppose it falls here then you cannot reject, you accept is not correct, but saying not reject is much preferable. Okay. Okay. Now, how does this chi-square distribution look like? The chi-square distribution is actually a very skewed distribution to the right, right. Now, it is a right skewed distribution whose shape depends solely on the number of degrees of freedom, right. As the degrees of freedom increases, so when r minus 1 into c minus 1 goes on increasing, this distribution becomes more like a normal distribution, right. So, you see when the degree of freedom is 2, this case, when degree of freedom is 3, when degree of freedom is 4, you can see the movement moving towards more towards the positive side, right. So, now slowly it will tend towards become the normal distribution. What is this phi coefficient when we calculate chi-square? The phi coefficient is a measure of the strength of association, strength is the strength of association in the special case of a table of with 2 rows and 2 columns. It is a special case of a chi-square where you have only 2 cross 2, it is a 2 cross 2 matrix. Okay. The phi coefficient is proportional to the square root of the chi-square. Now, that is why the formula is this, it is phi is equal to root over chi-square by n. So, it is the square root of the chi-square statistic, right. Now, what is this contingency table? We have, I will just show you the contingency table, something looks like this, right. So, there is the variable A and the variable B, right. So, you see when observations are classified according to 2 qualitative variables or attributes, the display is called a contingent table. So, whenever our case income and cleanliness, let us say are 2 qualitative variables which are measured in a maybe in a nominal way, right. So, then in that case this table is called a contingency. It is a cross table for displaying the frequencies of all possible groups of 2 variables. So, this is what I was talking about. So, R1, R2, R3 you have gone R let us say C1, C2 and goes on, and this is the total grand total. Okay. Variable A and B have been classified into mutually exclusive categories. The value O is the observed, right, frequency for the cell in row I and row and column J. So, let us say this is first row first column, right. So, you have a observed frequency. Similarly, for every one you have. The row and column totals are the sum of the frequencies. The row and column totals are the sum of the frequency. This is what I am talking about. The row and column totals are added up to get up a grand total of n, which represents the sample size. Now, the expected frequency is calculated as like this. So, row total into column total by grand total, right. So, in this case for example, if I want to measure the cell frequency of this one expected, so I will not take any other row, but only this row, the corresponding row, right, and the corresponding column, right. So, corresponding column. So, R1 into C1 by n. For let us say this case, right, this case it will be R2 into C2 divided by n, right. Suppose it would have been this one, let us say this case. So, it is R1 into Cc divided by n. So, it goes on, you can calculate. The procedure to test the association between two independent variables where the sample data is presented in the form of a contingency table is summarized as follows. First, state the null and the alternate hypothesis. Okay. What is this? The no relationship or association exists between two variables. The second alternate is a relationship exists, that they are related. Now, select a random sample and calculate the expected frequencies. So, the expected frequencies have been calculated for each cell and then we compute the chi-square value, right. So, when you calculate the degrees of, then you after you calculate the chi-square value, you calculate the degrees of freedom. So, we have seen how to do that. So, number of rows minus 1 and number of columns minus 1. So, now we use a level of significance and degree of freedom, we find the critical value for chi-square. And now from here, once we have calculated the critical value and we have the actual value or the calculated value, then we can compare and say whether the hypothesis is to be rejected or null hypothesis to be rejected or not rejected. Okay. So, and finally, when you compare the calculated table values of chi-square, decide whether the variables are independent or not using the decision rule except H0 if chi-square calculated is less than the table value chi-square alpha, which is as per this degrees of freedom, otherwise reject H0. Well, I will wind up here. In the next session, I will continue with this. We will start with an example, we will solve a problem from chi-square statistics and then we will get into some other non-parametric techniques, a few more are left and then we will wind up, and I will try to show you on the software also, and we will continue with it. Thank you so much for today.